In this clip, we want to discuss change of variables of double integrals, but I want to start out by reminding you how we do change of variables for single variable integrals, or maybe you called it substitution. It's the same thing. So let me write down the formula. The formula is sometimes more confusing than what's actually done, but nevertheless, it's important to understand. So here's a good old Calc 1 single variable function, and we want to calculate the integral, intuitively the area under the graph, between a and b. Okay, and the theorem, bless you, the theorem on changing variables says, okay, this is some expression with x's, that's what a function of x is. We want to take parts of it and call certain expressions with x, we want to call them, let's say, t. And we don't just replace x's with t's, but we have to do something more sophisticated. And what we have to do is whatever expression that we chose, we want to plug it into the function, and that expression is again a function. So it's the value of f at phi of t. And the range over which we're integrating now has to correspond to the new variable, and it's going to be some alpha and some beta, and I'll write in a minute how they relate to a and b. And then there's going to be the dt here in the new variable, and then there's going to be something else here, and that something else is the derivative of phi with respect to t. Okay, does everybody recognize this? Does it look familiar? Okay. And I'm not going to prove again why this is true and so on. It's really a rather straightforward consequence of the chain rule for derivatives. You just integrate both sides. What's important to know is that, first of all, the function you use to do the substitution has to be invertible on the domain. Sometimes you can weaken the assumptions slightly, but in general it has to be invertible, so phi has to be invertible. It has to be differentiable, because we're using its derivative. Okay? And the way these relate one to another is that phi of alpha is a, and phi of beta is b. That's how the domains relate to each other. Okay, so this is the change of variable formula for a single variable function. When you do it in examples, usually you write here under the equal sign. You don't state the formula every time. You just write under the equal sign, or in some other way. There are various ways of expressing it, but sometimes you just write under the equal sign. I didn't make a long enough equal sign. You write x equals phi of t, and then you write dx equals phi prime of t dt. Both of these do not make too much sense, right? Dx is just part of the notation for the integral. What does it mean for it to be equal to this? But it's just kind of nonsense that we write for ourselves to indicate that this is actually what's happening. We're replacing x by phi of t, and then we're replacing dx by phi prime of t dt. Okay, so this only makes sense for the theorem. Okay, clear? And one can define differentials and even make a bit of sense of things like this, but usually that's not necessary in order to do substitutions. Okay, does everybody know what I'm talking about? Is this okay? So the first thing I want to do is write this exact same thing a bit differently, in order for us to kind of see how to generalize it when there are two snakes here. So I'm not going to change anything on this side, but instead of phi, I want to call the function, I want to call it x. So I want to write x equals x of t. Okay, so do you think you're grown-ups enough to live with something like that? Okay, I'm replacing x with some function of t, which I'm going to call x of t. Okay, and then phi prime of t is going to be x prime of t But then I'm going to write it dx over dt, which is Leibniz notation for the derivative. Okay? So I'm going to write this exact same thing, but a bit differently. So the integral from a to b of f of x dx equals the integral from alpha to beta of f of x of t times dx to dt, and then integrating dt. Good? Do you see that it's basically the same thing? Okay, and again, there are assumptions here. X has to be a differentiable, invertible function of t on that interval, and so on. Okay. Maybe let's write that. Where x of t is differentiable and one-to-one on the appropriate intervals. Let's even add such that x of alpha is a and x of beta is b. Okay. So without really understanding why, let's try just to, in terms of the format, to write a double snake analog of this thing. And then we're going to see why that's true. Then we're going to state it as a theorem and prove it and even discuss the geometry that's hidden behind it. But let's first just try to understand what we're expecting. Okay, so for fxy, we expect, and this expect is rather we guess, we're guessing, something like, and here's our guess. So obviously there's going to be a double snake here instead of a single snake, right? The function is no longer going to be f of x, it's going to be f of x and y. And then it's going to be dx dy rather than just dx. And the domain is not going to be an interval from a to b, it's going to be some domain in R2. Do you agree? So that was the easy part. What do we expect on this side? Well, it's going to be a double integral, right? And the function is still going to be a two-variable function. But now, each coordinate, instead of x, we're going to write something of the form x of t. But here there was just t because it was just x. Here there are x and y, so there are going to be two new variables, and we're going to call them u and v. Okay? So each coordinate is now going to be replaced by a function of u and v. So we're going to have here x of u and v and y of u and v. These are the two functions that replace x and y. Okay? And then down here, we're going to have du dv instead of just dt, right? And the domain is going to be some new domain in the uv plane. D was in the xy plane. E is going to be some domain in the uv plane, which transfers, so these two domains by this map should transfer one onto the other, right? So if you take a point uv in E and you take x of uv and y of uv, you should expect to land in a point xy in D, and vice versa. Do you agree? Okay, so that's the generalization of this statement and of the entire interval. Does this make sense? I'm just doing it the very naive, unintelligent way. Well, slightly intelligent, but not formal. Okay? And there should be something missing here. That's why I left some space. And that something should be some derivative, right? And that derivative should be some derivative of the old variables, x and y, with respect to the new variables, u and v, right? And it is going to be something of that form. We're going to write it. I'm going to write something that we haven't seen before, and we're going to have to make sense of it. Okay? So I'll first write it, and then we're going to make sense of it. So it's written dxy to duv. And in fact, it has an absolute value, and we'll discuss it further in a minute. Do you recognize it? We have met it very briefly previously. Does it ring a bell? Very good. This we call the Jacobian. It was a 2-by-2 determinant of the partial derivatives of x and y, which are now functions, with respect to the variables u and v. We met it when we discussed the theorem on implicit functions and its consequence on the inverse function theorem. Ring a bell? Okay. So this is called the Jacobian and denoted by J. And in fact, it's J in absolute value. And we'll discuss everything here at length in a minute. Okay? So do you agree that at least visually, without understanding exactly what happened here, this is the formula we expect? This makes sense. Okay? This resembles this. Now we have to decipher it. Now we have to understand what's going on here, why this is true, understand the geometry, and so on. Okay? Clear, everybody? Okay. So let's add in the details. So this is the formula we expect. Maybe I'll just write the formal theorem, and then we'll fill in the details. So here's the theorem. Let x of uv and y of uv be in C1. So these are functions that are differentiable and have continuous partial derivatives. We want to take their derivatives, so this is obvious. And in fact, we're not just taking their derivatives, x with respect to u and x with respect to v. We're setting them up in a certain determinant, which is, that's not the point, but then we're integrating, right? So we want, the C1 here also makes sense, because we want to integrate these partial derivatives. And if they're continuous, then we know that they're integrable. Okay, so this requirement makes sense. Let be in C1 and assume that they define, these functions define a map, a correspondence, not just any correspondence, one-to-one invertible map, one-to-one map from the domain E in the x in the UV plane onto the domain D in the xy plane. Okay, so this defines a map that takes any point in E, which is of the form UV, plug it here, you get a point xy, and that point is in D. Okay, and it's one-to-one and onto, so it goes backwards as well. Okay. Also, assume, so this is again a requirement that we're going to have to check that it's satisfied whenever we use this theorem, that the Jacobian J, which is dxy to duv, and let's write explicitly what this means. It means the determinant x u x v y u y v. This is what this notation stands for. So another assumption is that the Jacobian is not zero in E, in the domain we're discussing. Okay, so each one of these is going to be a function of u and v, right? The partial derivatives are again two variable functions of the variables. Okay, so here we're going to get some expression with u's and v's, and we want it to be non-zero in the domain E. Okay, and we'll see why it's important for it to be non-zero also. Everything here we're going to discuss. Then, so if all of this is satisfied, then we have the formula that we wrote on the previous board, and I'll write it again. Double integral over the domain D of fxy dx dy equals the double integral over the domain E of f of x uv y uv times the Jacobian in absolute value du dv. Okay, so this theorem is a mouthful. It really is. And before we understand the geometry and understand some phenomenon that's going on here, why are we requiring this to be non-zero? How does it relate to the fact that this is an invertible map? All these little details, which we are going to understand them. We are going to make efforts to understand them. I want to do one or two examples to see that it's not as scary as it looks. Okay, that's always good to do examples and see that we can handle it. And then we'll go back to the theorem and discuss the more theoretical aspects of this theorem. Okay, so let's do an example. Here's our first example. Just maybe before the example, of a couple of short remarks. Of course, we want to use this. When will we do things like this? Only when we have we find a substitution, we find a change of variables such that this is easier to calculate, right? That's the only reason to do a change of variables, okay? And another remark, I wrote it here assuming certain assumptions, which are the easiest to express and the most straightforward. One can weaken them a bit, make the theorem stronger. So for example, and that's an issue that I'm not going to get into the details of, I just want you to know. Here I require that J is non-zero on the entire domain. That's the easiest thing to say. One can weaken that. One can require that it's non-zero, except maybe in finitely many points. Or except maybe on a curve in a domain, which makes no difference in terms of the integral. Okay, the integral is something two-dimensional. If you take a one-dimensional object inside, the integral doesn't see it. Okay, just like when you take a single variable function and you change its values on points, the integral, the area under the graph, doesn't see what happens when you change the value of the function on isolated points. Okay, so that's just a remark. Maybe I'll write it down. So remark. It suffices to require that J is non-zero except on finitely many points or on a curve. So there's a more precise way of stating this. So you can allow J to be you can allow J to be 0 on a domain which has what's called 0 area. Okay, but we didn't define that precisely, so I don't want to say it precisely. So if it's like on a one dimension less than the dimension you're dealing with, so if you're dealing with a domain in 2 dimensions, which has area, if you can allow J to be 0 on something which is 1-dimensional, okay, or 0-dimensional, like a point. Okay, so let's do some examples. Let's do them in a separate clip. So we'll stop this one here.